In the previous video, we have shown that all bases of a vector space must have the same number of vectors. This number, n, is called the dimension of V, written as dim V equals n. The dimension of the zero vector space is defined as 0. If V has a basis of finitely many vectors, in other words, a finite basis, then V is called a finite dimensional vector space. Let's look at a proposition. R bracket x is not finite dimensional. To prove this, suppose for a contradiction that R bracket x is finite dimensional. Then R bracket x is spanned by finitely many polynomials, say f1 of x, f2 of x, up to fn of x. Let d be the maximum degree of these polynomials plus 1. Then x to the d is not a linear combination of f1 of x, f2 of x, up to fn of x. This is a contradiction which completes the proof. Let's look at the following theorem. Suppose V is the span of V1, V2 up to Vn. Then there exists a subset of V1, V2 up to Vn, which is a basis of V. Also, the dimension of V is less than or equal to n. The proof of the first point is known as the casting out process. If V is the zero vector space, then there is nothing to prove. So assume V is not the zero vector space. We start from V1, V2 up to Vn. If V1, V2 up to Vn is linearly independent, then it is a basis of V, and the dimension of V equals n. Otherwise, we can find λ1, λ2 up to λn in F, where at least one of them is non-zero, such that λ1 v1 plus λ2 v2 plus up to λn vn equals the zero vector. By reordering the vi's if necessary, we may assume that λn is non-zero. Then vn equals negative 1 over λn times bracket λ1 v1 plus up to λn minus 1 vn minus 1. So Vn is redundant, and V is the span of V1, V2 up to Vn minus 1. We can continue this process to reduce the number of vectors in V1, V2 up to Vn until the remaining subset is linearly independent. Note that we can do so because V is not equal to the zero vector space means that Vi is non-zero for some I, in which case Vi is linearly independent. Since this subset still spans V, it is a basis of V. For the second point, since any basis must be linearly independent, we know from a previous lemma that the size must be less than the size of a spanning set. In other words, the dimension of V is less than or equal to n, and this completes the proof. Let's look at an example. Let V be r to the 4. Consider V1 equals 1, negative 2, 3, 1, V2 equals 2, 2, negative 2, 1, V3 equals 5, 2, negative 1, 3, V4 equals 11, 2, 1, 7, V5 equals 2, 8, 2, 3, and let W be the span of these vectors. We want to find a basis of W contained in V1 up to V5. We set up a matrix with rows V1 up to V5, and reduce it to row echelon form. So V3 and V4 is in the span of V1 and V2, and V1, V2, and V5 are linearly independent. This means that the span of V1, V2, and V5 equals W, and V1, V2, and V5 is a basis of W. Let's look at another theorem. Let S0 be the set, W1 up to Wm be a set of linearly independent vectors in V. Then V has a basis containing S0, and the dimension of V is greater than or equal to m. To prove this, let the dimension of V equals n, and V1 up to Vn be a basis of V. If V1 is in the span of S0, then define S1 equals S0. If V1 is not in the span of S0, then define S1 to be S0 union V1. Repeat this for v2 up to vn. We claim that each Si is linearly independent. We proceed by induction on I. S0 is linearly independent by assumption. Assume inductively that Si-1 is linearly independent. Let Si-1 be equal to the set U1 up to Ut, and lambda1 times U1 plus up to lambda t times Ut plus alpha times Vi equals the zero vector. If Vi is in the span of Si-1, then Si equals Si-1 is linearly independent. If Vi is not in the span of Si-1, then alpha is equal to 0. So, lambda1 times U1 plus up to lambda t times Ut equals the zero vector, and since Si-1 is linearly independent, this implies that lambda1 up to lambda t are all equal to 0. This means that Si, which is Si-1 union Vi, is linearly independent. Now, S0 is contained in S1, is contained in S2, and so on. So for all I, Vi is in the span of Si, which is contained in the span of Sn. So, V is the span of V1 up to Vn, is contained in the span of Sn. Also, Sn is linearly independent, so Sn is a basis of V. Then, the dimension of V, which is the size of Sn, which is greater than or equal to the size of S0, which equals m, and this completes the proof. Now we are ready to prove this important theorem. Let the dimension of V equals n. Any spanning set of V with n vectors is a basis, and any linearly independent set of V with n vectors is a basis. In other words, if we have a set with the size equal to the dimension of V, for this set to be a basis, we only need to show that it is a spanning set or a linearly independent set. This saves the work of having to show both conditions. For the proof, we know from the first theorem that any spanning set contains a basis, but any basis has n vectors, so the spanning set is already a basis. For the second point, we know from the second theorem any linearly independent set is contained in a basis, but any basis has n vectors, so the linearly independent set is already a basis. And this completes the proof. Let's show one more theorem. Let W be a subspace of V. Then the dimension of W is less than or equal to the dimension of V. Also, if the dimension of W equals the dimension of V, this means that W is equal to V. To prove this, if W is the zero vector space, then the dimension of W equals 0, which is less than or equal to the dimension of V. If W is not the zero vector space, then there exists a vector W in W, and it is not the zero vector, so W is linearly independent. Now, W is contained in some basis B of W. Since B is linearly independent in V, its size must be less than a spanning set in V. In other words, the dimension of W is less than or equal to the dimension of V. Now, if the dimension of W equals the dimension of V, then B is a linearly independent set in V with the dimension of V number of vectors. So by the previous theorem, B is a basis of V. Then W, which equals the span of B, is equal to V, and this completes the proof. Let's end this video with an example. Let's classify all vector subspaces of R3. First, note that the dimension of R3 equals 3. Let W be a subspace of R3. From the previous theorem, we know that the dimension of W is 0, 1, 2, or 3. If the dimension of W equals 0, then W is the zero vector space. If the dimension of W equals 1, then W is the span of one non-zero vector, say W. So W is a line passing through 0. If the dimension of W equals 2, then W is the span of W1 and W2 for some linearly independent W1 and W2. So W is a plane passing through 0. If the dimension of W equals 3, then we know from the previous theorem that W equals the whole of R3.